Hello, everyone, and welcome to the OneClass channel. My name is Donna Riel, and I'm a recent master's graduate from the Materials Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. So now let's just get started on our set of questions for today's session. Okay, so question 1 just asks, what is a Haworth projection? Okay, so a Haworth projection this is typically used to depict cyclic sugars. People note that it is less complicated than chair conformations and they still keep the orientation of your OH functional groups. Okay, so I'll have an example of how to convert a Fisher projection to a Haworth projection. So from a Fisher projection, I'll just draw the starting Fisher projection. Let's say we had carbon, and I'll just have an example with all the different orientations of the alcohol group. And for the first part, we want to rotate the bonds around carbon 5 clockwise. Okay, so I'll show the rotation. So first, let's number them. So the carbon with the aldehyde group will be carbon 1. And then I'll just number them going down. So carbon 5 is right here. And I'm just going to rotate all of the functional groups on carbon 5 in a clockwise manner. And then I will write what the product looks like. So I'll try to fit it here. Oh yeah. So now this is carbon 5. So let me just rewrite the order. So there's a hydrogen now on this right side. The OH is pointing down. And the last carbon alcohol group is just kind of on this side. Like that. So now I'll just write step 2 up here. You'll write the arrow going up. Okay, so step 2 is to turn the whole molecule clockwise on its side. So I'll draw that right below it. So if we were to rotate this whole thing, try to show like an arrow. Rotating it on its side. So this is carbon 5. And let me just also number them so that we can see where all the carbons go. So this is now 6, 5, 4, 3, 2, and then 1. So step 3 is to draw a hexagon and to omit the line connecting carbon 1 and 6. So if we draw out the hexagon, kind of looks like this. But then step 4 is to just add all of the OH groups and CH2 groups with the same orientations. So I'm just going to show that carbon 6 is up here. And then we have an OH group. So let me number them again, just so that looks a little less intimidating. So on this is carbon 5. This corresponds to this carbon. Carbon 4 has an OH group pointing down. Carbon 3 has an OH group going up. Carbon 2 has an alcohol group going down. And then, yep, so I'm not going to connect carbons 1 and, well, 6 just yet. I'll do that in the next step. Which is just to connect the alcohol group on carbon 5 with carbon 1. So now we have proper hexagon. And the rest of them just stay the same. So you can also draw in the hydrogens, but for the sake of like clarity, I'm just going to leave it be and show just the alcohol groups. So I'm going to show the alcohol group on carbon 1 pointing down, but note that for this example, it can point either up or down, just because it wasn't specified when it was a carbonyl. And then this is the finished Haworth projection. So let me just add a little side note that the OH group on carbon 1 can be in either direction. Okay, so these are all the basic steps on how to convert a Fisher projection to a Haworth projection. And let's see what the junior tutor said. Haworth projection is a way of writing a structural formula of cyclic monosaccharides in a three-dimensional formation. This structure still keeps the stereochemistry of each bond. Shown below is the Haworth projection of D-glucose. Yep, so this solution is correct.